Okay, so let me begin as promised with a short demonstration of how bosons and fermions are different. I'm going to show you two experimental results from about 20 years ago, so quite recent actually. And both of these are from the field known as cold atoms. By accident, it's the field I work in, so that's the experience I know. But the idea of this field of research is that you have a gas of atoms, and it's a very dilute gas. So the density is very, very low, and that's why when you make it very cold, it still remains a gas. Regular gas, when you cool it down, becomes a liquid and a solid, but these gases are so dilute that even at temperatures very close to the absolute 0 Kelvin, so at temperatures of a microkelvin or a couple of hundred nanokelvin, they are still gases. And on the other hand, when you cool down a gas, the Broglie wavelength becomes very large, so you see quantum phenomena inside a gas, right? That's the way to do it. So typically in these kind of setups, you have a harmonic trap. So this would be a harmonic trap, and then the temperature is at some energy, and let's say in this case it's not cold enough yet, and the gas still behaves classically. So the velocity distribution of velocities will follow a Maxwell-Boltzmann distribution, and I kind of illustrate this with the little particles flying around, and in this case you know their position and their momentum simultaneously because it's a classical gas. The question is what happens on the size of the gas, obviously, is more or less where the temperature, right, where the particles turn around. They cannot go beyond this point because their kinetic energy doesn't allow them to go higher up in the potential. So the size of the gas that you observe in the lab is given by the temperature, right? Just so you have an idea, in a typical setup in the lab, this size of the gas is about a centimeter order of magnitude. So you actually see this with your bare eye. So what happens if you cool down the system? Now you're cooling down, so I'm going to move the temperature to a lower value. So two things happen. First of all, quantum mechanics starts. When quantum mechanics starts, your energy levels start becoming discrete. So you cannot talk of velocity at position anymore, but you have to start talking about energy levels. And because this is a harmonic trap, you get equidistant energy levels. But the way the particles are distributed inside the trap depends on whether they're bosons or fermions. So if they're bosons, multiple particles can be in the same state, so the ground state, first excited state, and so on. And the size of the gas is given more or less by the particle that is the most spread out in the trap. And in this case, the highest populated state is just given by the temperature. So the gas, as you cool it down, will shrink, will become smaller. On the other hand, if you're working with fermions, even though you lower the temperature, the number of particles will now give you the highest level, because you're fermions, by the exclusion principle. And the size of the gas will remain larger than the case of the bosons. Right? And the important thing to stress here is that these are not interacting particles. So it's not the fact that fermions are bumping into each other that creates some kind of pressure and pushes them out. These particles are not interacting. This works in as I said, it's a dilute gas. These particles never touch each other. They never bump into each other. Each particle is an individual and doesn't know the others exist. The only thing it knows is that it's a fermion and it has to obey fermionic statistics. So this is due only, this is a result which is due only to the quantum statistics and not due to interactions.
Will in the fermionic rock, it will remain in the state?
What do you mean?
Each and every atom will stay in
Are you asking if they can switch position?
No, if they are like falling down or something, or they're occupying state.
They're occupying a state. So the wave function of this particle will be a Gaussian, right? The ground state of a harmonic oscillator. This will be x times the Gaussian. This is x squared times the wave function. right? The Harmonic polynomials. And so the extent of this wave function is much more than the extent of this wave function. If you look at your harmonic oscillator wave functions. So they all occupy different harmonic oscillator states. And this one is much wider than any one that is here. And that's why in the gas it is much, much larger. So let me show you this in an experiment. So these are pictures taken with a camera of atoms. It's a false color image. Blue means there are no atoms, so the density is 0. And the more it gets, the more red it gets, the higher density. Okay. Lithium-7, these are both lithium atoms, but lithium-7 is an isotope which is a boson. Just count the number of electrons and protons and neutrons. You'll find an even number, so they're bosons. In this case, you find an odd number, and in this case, that's why it is a fermion. And at these temperatures, this gas still behaves classically, so it's an active Boltzmann distribution, and both gases are more or less the same size. Now I'm going to cool down the system, both the fermions and the electrons, and again take images at different temperatures. So as you see, the bosons become smaller, they collapse towards the center of the trap, whereas the fermions, although you're here, this is the same temperature, just in units of the Fermi temperature, energy of the highest level. Even though you're far below the Fermi temperature, the gas is still more or less the same size as the classical gas. Once again, this is not interactions, there's nothing pushing against each other, it's purely the quantum statistics that does this. This is 100% quantum mechanics. Okay? That's the first result. This is from 2001. You have the reference if you want to read the article and get lost in technical details. So that's number one, which basically shows you the Pauli exclusion principle in position space. The second thing I'd like to talk to you about is something else, the Henry-Brown twist effect, which, by the way, are two people. Henry-Brown is one person, twist is the second person. Yeah, two last names for some reason. So what we're going to look at is so here you have a system of two particles, which are located at position x1 and x2, and they are in two different states, alpha and beta. Then the total wave function will be the either symmetrized or anti-symmetrized wave function, did you know? And I want to ask the question, what is the correlation, what is the probability for detecting the two particles simultaneously at two specific positions? In other words, if I have detected a particle at position x1, what is the probability of detecting the second particle at x2? And especially what happens if x2 becomes equal to x1? Right? So in order to think about this question, let's just first of all define the probability of detecting x1 and x2 simultaneously is just the absolute value squared of this wave function. And the probability, we have to normalize its correlation function. So we're going to have to normalize it by the probability of detecting just one particle at x1, which is the wave function integrated over the other variable. So, and the way this correlation function is defined is simply the joint probability divided by the individual probabilities. That's how it's normalized. Otherwise, obviously, if you have more particles, there's a high probability of finding it at a certain place. This way I normalize it by the probability of finding a particle, and you lose these effects. So let's first of all think about what would happen in a classical gas. What happens if there are no correlations, or there are no bosons, no fermions, they don't know about each other in any way, and they're just classical particles. Well, in this case, the probability of detecting a particle at x1 and one at x2, it's uncorrelated. So it's the product of probability of x1 being here and x2 being here. So if this thing is equal to the product, it's just equal to 1. Right? That means there's no correlation. But if you do this with this wave function, and I encourage you to go through the math, and you take the limit that x1 and x2 are equal, in the case of fermions, you get a number that is smaller than 1. Depends on what wave function you choose exactly. And in the case for bosons, you get a number that is larger than 1. So the first thing that is, you notice fermions smaller than 1 means that there is, if you detected one fermion at a certain position, the probability of detecting another fermion right next to it is small. And why is that? Because of Pauli exclusion. That we already know. It's not surprising. What you notice is that bosons have the opposite effect. So if you've detected a boson at a certain position, the probability of having another boson right next to it is enhanced. So this effect with bosons is called bunching. They like to appear in bunches, they like to appear together. And the effect of fermions is called anti-bunching. Here's the measurement from 2007. So this is simply the correlation G2 measured as a function of the separation. For here it's done with helium atoms. Helium-4 is a boson, helium-3 is a fermion. Far away, it's equal to 1. This is 1, this is 1. Just two different plots. For bosons, as you get closer, the number is larger than 1. For fermions, you measure less than 1. Anti-bunching and bunching. Again, this is a non-interacting gas. The non-interaction properties are bumping into each other. It's purely the quantum statistics that we see this. Okay? Are you fascinated? Let's do some math. So today we're going to start talking about interactions. First topic of the day. Okay, so we're going to talk about a free electron gas, the Mott-Hubbard transition, which will be a nice example for second quantization with interactions. And then we're going to talk about Wick's theorem. We're going to show you an example of how it works and prove the theorem, which I think you were promised by Efrat I would do. So I'm going to try and keep her promise. Okay, so let's start with the free electron gas with interactions. So the Hamiltonian of the system consists of two parts. There's the non-interacting part, which is simply the sum over all kinetic energies. So it's the number operator where you check at each momentum space, scanning the entire space in momentum space, and then put in the correct number for the energy, where epsilon k is just kinetic energy. The interaction let me write it in position space. So remind you of the way to read these kind of expressions. Remember, this is a metal detector or a particle detector. It goes around all of space. You look for a particle. It will beep when at position r it detects a particle. And you're summing over the entire space. That's what the integral d3r means. You're taking this operator, going all around space, looking for a particle at r. If you found one, you move on to the next operator. You again go over all of space and detect a particle at r prime. Only if you detect two particles, one at r prime, then you can continue. You put in the interaction energy, which is the Coulomb energy, and then you have to put back your particles at the same place where you took them away. And after you sum the overall space, you're going to detect all pairwise interactions. So this VEE is just a Coulomb interaction. And I'm using the convention where I'm calling E squared is equal to the charge squared over 4 pi epsilon 0. That way I don't have to worry about stupid constants. So just to make it a little easier and not to get confused with primes and no primes, I'm going to add indices 1 and 2. So this is going to be R1, this is going to be R2, R1, R2, and then 2 and 1. What we would like to do with this, and I think it was also promised to you by a thought, which makes a lot of promises, we want to put this into momentum space. And the reason we would like to do so is because the self-energy, H0, is diagonal in momentum space. So this you already did. And now we want the entire Hamiltonian in the same basis, so we're going to transform the interaction into momentum basis as well. And in order to do this, it's actually quite simple. All we have to do is replace our operators by operators that create particles in K-space. Dagger. Okay, so what this means is that this operator creates a particle at position R, and this operator creates a particle with momentum K. And as you know, if you know the position, you don't know the momentum, the opposite, and that's why if you create a particle at position R, it's in a superposition of momentum states. And this is just the eigenfunction of position of the momentum operator. That's why you have this Fourier transform to get from one to the other. Now we have to plug this into here, and we have 4, or 2 plus 2, in total of 4 operators. So we'll have to use this 4 times, and we're going to have to use a different K every single time so that we don't confuse the 4 sums over the 4 different Ks. So I'm going to call them K1, K2, K3, K4. Get ready for a long expression. So VEE. And by the way, this 1/2 that you always write in the beginning is to avoid double counting, right? Because both R1 and R2 are summed over the entire space. So you're counting everything twice, so you have to divide by 2 in the end. So in the first step, I'm just going to plug in this expression. So instead of psi dagger AR1, I plug in this sum. There's a 1 over L to the 3/2. And L is the quantization, or L to the 3rd is the quantization volume. So there's a sum over K1, e to the minus I K1 times R1 a K1 dagger. And there's another one of those, so there's the 1 L to the 3/2 sum over K2 e to the minus I K2 dot R2 a K2 dagger. Then we have the interaction itself, VEE of R1 minus R2. And now we have 2 more, and instead of for psi without the dagger, is, let's say, the complex conjugate, so we have no dagger here and a plus sign in the exponent. So this is multiplied by 1 over L to the 3/2, sum over K3, e to the I K3, and this is R2, A K3. And then 1 over L to the 3/2, sum over K4, e to the I K4 times R1, and destroying a particle at momentum K4. So that's the stupid part, just plugging it in. The goal is now to move everything that does not depend on position to the beginning, and then move the integrals forward so that you integrate over space only. And in this way, we will try and find a delta function. As soon as we have a delta function, delta in K, we'll be able to get rid of some of the sums. So let's do this. So this is equal to 1/2, and then we have 4 sums over K1, K2, K3, K4. And then the operators do not depend. What is this? K1, right? The operators do not depend on position, so we can take them outside the integral. So we have a K1 dagger, a K2 dagger, a K3, and a K4. And then there's an integral d3r1 over L to the 3rd, and integral d3r2 L to the 3rd. And now we're left with our exponents. I'm going to group them together as well. There are 2 exponents with R1 and 2 exponents with R2. So I'm going to group them together. K1 minus K4 times R1 and e to the minus I K2 minus K3 times R2. And then we have the potential R1 minus R2. So the potential only depends on the distance between the 2 particles. And this encourages us to introduce a new variable, which is the relative coordinate. So I'm going to introduce a new variable, r, which is the relative coordinate, r1 minus r2. And when I plug that into the expression, so let me just take for now only the integral part. Let's deal with just this for the moment, including this. So there's an integral. So what is the idea? The idea is that instead of using R2 and R1 and R2, I can use R and R1. So it's a change of variables, and I still remember 2 variables. And the Jacobian of this transformation is 1. So it's a very simple transformation. So there's an integral over d3r1 and d3r. There's no R2 anymore. And every place where I see R2, I'm going to replace it by R1 minus R. Right? So you get e to the minus I K1 minus K4 times R1. That remains. And then in the second experiment, there's an R2. So that's e to the minus I K2 minus K3. And instead of R2, I have to write R1 minus R. And then the potential is now a function of just R. It's starting to look good. Now let's take the stuff that does not depend on R1 before the integral and integrate over R1. So this is equal to the integral d3r over L to the third. So this part here times R depends on R. So that's e to the I k2 minus k3 times R. And then there's an integral over R1. And we can group all of the k's together. There's a k1 plus k2 minus k3 minus k4 times R1. And the potential only depends on R, so that goes in here as well. Sorry, forgot about that. Here also have the potential. So this is exactly what we wanted, right? This is the definition of a delta function of the argument here in the brackets. So this is a delta function k1 plus k2 minus k3 minus k4. And of course, the physical meaning of this delta function is conservation of momentum. If k1 plus k2 is different from k3 plus k4, the entire operator is just zero. Nothing happens. Only if momentum is conserved, the interaction is legal. So let's make another substitution. I'm going to denote by Q this difference here, K2 minus K3. And by means of this delta function, this is the same as K4 minus K1. So now I can write the interaction term. I'm going to put back in all of the sums and all of the creation and annihilation operators. And I'm going to compute one of the sums. Say over K1, I can compute the sum and use the delta function. And then I'm going to use this substitution to get rid of an additional index or replace one of the additional indexes. So what you get is 1 over 2 L to the third. We still have an L to the third left from here. This one went away in the delta, but we still have one volume left here. Summing over K3, K4, and over Q. And creating. So the first operator here created a particle with momentum K1, but K1 is equal to K4 minus Q, right? And then the second creation operator creates a particle in K2, but again, I can write K2 as K3 plus Q. I'm leaving K3 and K4 in the annihilation operators. And then what's left is this integral. Sorry. No division. It's this integral, and then e to the I, but K2 minus K3, that is Q. So it's e to the I QR. times the potential VEE over R. Yep.
Can you explain again why we make a transition as Q is equals to K to -K3 and...
So this is my definition of Q. I'm defining that this because it appears here.
Why is that the definition?
My choice. I'm introducing a new variable Q, and I choose it to be equal to K2 minus K3.
Why?
Because it appears here, and I don't want it appearing here. I want to have only one variable here. It has a physical meaning as well, which I'll show you in a second. But for now, if you don't know what the physical meaning is, just for my own comfort, exactly, I'm replacing this by Q. And then it is equal to K4 minus K1 because of the delta function.
Yeah,
Right, so this step is obvious. And then when I do the sum, I've computed the sum over K1, for example, and instead of K1, I then write minus K2 plus K3 plus K4, and then I replace K2 and K1 by Q and whatever it is. This is what we end up with. So we're almost done. There's still R over here. We have to get rid of that. But this is simple. That shows a Fourier transform. So I remind you that this VEE is just E squared over R. So what is the Fourier transform, the three-dimensional Fourier transform of 1 over R? No one remembers. Very good. It's 1 over Q squared. You can check. This is an exercise in second year. Allow me to skip that. And we can now write down the final solution, and then we can interpret it. One last convention, just symbols. I'm going to rename K4 as just K. And I'm going to rename K3 as K prime. So I'm back to my primed coordinates. There we go. And I'm missing a vector. Okay, now let's try reading this expression from right to left. We run around the entire space. We detect the particle with momentum k. We detect the particle with momentum k prime. We now put in some interaction energy, which could be anything basically, because q is also summed over. But then we have to put the particles back at different momenta. One of them we put back at k plus q, and the other one we put back at k minus q. This gives you the interpretation of q. It's the momentum is transferred during this process. So what this describes is a scattering process, a collision process. And the very interesting thing that happened here is the following. In momentums, in position space, you detected two particles at R1 and R2, and you put them back at R1 and R2. So the particles didn't move around. It's a local interaction. It does not change the position of the particles. But in momentum space, you destroy particles at k and k prime, but then you put them back at different momenta. So it is non-local in momentum space. A lot of math, but actually quite simple. Questions? Great. Let's move on to Hubbard. So I'm writing down the Mott-Hubbard Hamiltonian. And I'll explain the system in a second. What is the Hubbard Hamiltonian? What does it describe? So imagine a one-dimensional lattice. So we're back to solids. And think about the tight binding model that you know from solid-state physics. So you treat each site, or each of these wells, you treat as a site. This is site number A, this is site A plus 1, this is site A minus 1. And this first part of the Hamiltonian, HT, is what we call the hopping term, and it is exactly the same as the tight binding Hamiltonian that you know from solid-state physics. The only difference is that now I've written it in terms of creation and annihilation operators, and you're used to saying it in terms of bras and kets. But if you replace your bras for annihilation operators and your kets for creation operators, you will see that it's exactly the same Hamiltonian. The only thing I've added, I'm not sure if you did spin and tight binding, maybe not. So the only thing I've added is a spin index, but notice, very importantly, that this is a particle hopping from site J to site I, but it's the same spin. There's no primes in the sigma. It's sigma, sigma. So a particle which is up in one state will hop to the other state and remain in the same spin state. Okay. There's no spin flip. The addition, so this first part is very simple. You know how to solve it. It's tight binding. You've done it a million times. That's the easy part. What makes it more complicated is the second term. That's the interaction term. And it tells you that when two particles are on the same site, then they have an interaction energy U. Now, we are talking about fermions, and they are spin 1/2 particles. So this is just known as an electron. So the largest number of particles you can have on a single site is 2. You can have one up and one down particle on the same site. You cannot put another particle onto that site, right? That's Pauli exclusion. But if you put two particles on the same site, you pay for this with energy, energy U. So that's interaction energy. The energy is higher as soon as you put two particles on the same site. Okay? Great. Now, for illustration and for the math and stuff we're going to do now, we're going to limit ourselves to the simplest possible lattice, which is a lattice with two sites, site number 1, site number 2. In this case, I can even write out the Hamiltonian. So this will be minus T. Then there are 4 operators. 2 up, dagger 1 up. So this is an up particle hopping from 1 to 2. And then this up particle can also do the opposite. It can hop from 2 to 1. So you create it at 1 and destroy it at 2. And the same thing can happen for a down particle. So you can create a down particle in lattice site number 2 and destroy it on number 1. And it can go the other way. You can create it on 1 and then destroy it on 2. Again, I'm stressing when it hops, it remains in the same spin state. The interaction Hamiltonian in the case of 2 sites is also simple. You count the number of up particles and the number of down particles on site 1. If both are equal to 1, you get U. If either is equal to 0, it's 0. Right? And the same thing for site number 2, up into down. Okay, what is the maximum number of atoms I can put into this 2-site model? Right? I can put an up and a down on number 1 and up and down number 2, and that's it. System's full. What happens when I put, what is the energy when everything is full? So the hopping term contributes 0 to the energy. You're always applying at least 2 creation operators to the same site, right? And the interaction energy, you get 1 from here and 1 from here, so the energy is equal to 2U. And there is no motion. No electron can move anywhere. And when electrons cannot move, we call this an insulator. So in this case, you have an insulator. On the opposite extreme, we can have 0 particles. That's a stupid case. Energy is 0. But also here we have an insulator. Nothing is moving because there is nothing. But what I'm trying to tell you is that this is a certain type of insulator, which we call a band insulator. That's actually the only type of insulator that you met in solid state. N equals 4 means that the band is full. Remember that tight binding is an approximation for a single band, but you have a bunch of them. So if a band is full, you get an insulator, and when a band is empty, you have an insulator. So it's called a band insulator. Any other case, so N equals 1, 2, or 3, you get a conductor. Because there's always at least one particle that can move around. Right? Except there's one exception. And that's the states we're going to talk about. We're going to focus today on the situation for N equals 2. And for N equals 2, you can create a state that is also insulating, and this is known as a not insulator. So this happens when N is equal to 2 and the interaction is much larger than the hopping. In this case, you get what's called a not insulator. So although the band is exactly half filled, and you would expect there to be conductance, you actually get an insulator. And I'm going to show you some head-waving arguments to justify this, and then I'm going to do some calculations to justify it even more. So the first way to think about it is actually quite simple. If the interaction energy is much larger than the hopping, then as soon as you put 2 particles on the same site, they will redistribute to be so the point is that the number of particles is equal to a number of sites. So the system will be preferably be in a state where there's exactly 1 particle per site, and none of the particles wants to move to the neighboring site, because it will only gain energy T, right, negative. It likes to hop because it's negative energy, but it has to pay for it with energy U. And if U is much larger than T, that just isn't worth it, and it won't hop. So in this case, each particle is at a specific state, at a specific site, and it doesn't want to go left or right. No motion, again, in an insulator. What maybe the more surprising thing is, and this is what I'm going to prove to you in the next few minutes, is that the not insulating state has anti-ferromagnetic ordering. So it will be up, down, up, down, up, down. And this is what we're going to tackle now. Let's forget about u larger than t at the moment. Let's just assume that we have u equal to t or any relation between the two. None of them is especially strong or especially weak. And we're putting two particles on two sites. Any two particles on any two sites. We spin up and spin down. So what is the total number of possible states with the constraint that n is equal to 2? Getting complicated, eh? Let's try and count them step by step. We have spin polarized states. Spin polarized states means that we have either only ups or only downs. And this is only possible if they're on different sides. So P1, which is the first polarized state, is A1 up and dagger and A2 up dagger acting on the vacuum. That's two particles, one up, two ups, one on number 1, one on number 2. And the second possibility is to have two downs. Then we have the case of regular single occupancy states. So there's only a single particle per site, but without the convention of spin polarizing. So we can have either an up on 1 and a down on 2, or the opposite. Down on 1 and an up on 2. And the third case is the double occupancy. We have two particles in the same state, sorry, two particles on the same site, but in this case I must create one in the up state and one in the down state. I can do this for either one of the sites, either site number 1 or site number 2. I now adopt the convention for the Fock states. So I'm going to write the Fock states as the number of particles on lattice site 1 in state up, and then 1 and down, and then 2 and up, and then 2 and down. So then this is state 1, 0, 1, 0. This will be state 0, 1, 0, 1. This will be 1, 0, 0, 1. It's going to look like computer code. 0, 1, 1, 0. And there's 1, 1. 0, 0, and 0, 0, 1, 1. Any other options to put two particles on the two sides? Shout if there is. No one's shouting? Okay, I don't see any either. Okay, now.
The second line, the single occupancy.
Yep.
There will be like A1 and A1 down, A1 up, A1 down.
So that one's here, but that's a double occupancy because there are two particles on the same site.
Yeah.
Right, single occupancy means one particle per site.
Okay.
And this means two particles per site. Right. So let me ask a different question. Which of these states are eigenstates of the Hamiltonian? I'll give you a hint. The state has zero energy. Both the interaction and the hopping is zero. Who says spin polarized? Who says single occupancy? Who's asleep? Everyone. Who says double occupancy? Let's try. It's not the third one, okay. But you can hop, right? And the third one you can hop, so it's definitely the third one. Excuse me? So they're in the same place. Okay, same argument, yeah. Same place, so you have U. What about this state? They can hop, so they have energy of at least minus T, and they can hop back and forth, so it's minus 2T. At least, right? What about this state? They can't hop because they're all spin polarized. There's no double occupancy, so the interaction is zero. So this is E equals 0, and it's an eigenstate of the Hamiltonian. It's the total Hamiltonian. Now, because the Hamiltonian has a term that is negative, right, I would think, that, if I wouldn't think, I could come to the conclusion that E equals 0 is the ground state, because it's zero energy, right? But that's not the ground state. The definition of the ground state is the lowest energy. Negative is smaller than 0, right? So, and in the Hamiltonian, the hopping term has a negative contribution. So it is possible to create a state with negative energy, which will be the ground state, and it has to be a superposition of these four states, because these are already eigenstates. Think about Hamiltonian as a 6 by 6 matrix, then the lines with P1 and P2 are already diagonal, it's block diagonal, and the one with these four, so this can become this, right? If you hop in the correct way, then yeah, this can become this, because this is up on 1, it can hop to particle number 2, so the hopping term can take S1 to D2, right? So there'll be off-diagonal terms for this block, but the upper two states are already diagonal. So the actual ground state with the new eigenenergies has to be a superposition of the S1, S2 states and D1, D2 states. Okay? So far you follow? The simple way to find it, well, simple, the QM1 way to find it is to write out this matrix and diagonalize. It's a 4x4 matrix, it's not that complicated, it can be done. But what if I want you to do this for a a real model which has 300 sites? So you're not going to diagonalize that, and that's why we're going to have to use some more intelligent method of doing this. And the procedure is the following. By the way, if you think about it for a second, you can already kind of predict the answer. As was already pointed out, D1 and D2 have interaction energy U, at least U, because they're on the same site. We're now going to take the limit where the interaction energy is much larger than the hopping term, as I already said we would at some point. So we expect in the eigenstates that the main contribution comes from S1 and S2. So if you write the eigenstates as a superposition of A times S1 plus B times S2, or C times D1 plus D times D2, right, some coefficient, we expect the coefficients of the S states to be much larger and the coefficients of the D states to be much smaller. And the limit where U is much larger than t, then these just will become 0, and these will become, well, half each, or some way that they add up to 1, or that their squares add up to 1. So we expect the main contribution to come from the single occupancy states. And if you look at the single occupancy states, they're exactly as I predicted. They are antiferromagnetic. They are up on site 2 and down on site 1, or the opposite. So from the simple argument, you can really more or less predict the answer that the Mott insulator in this limit becomes antiferromagnetic. But let's do this a little more mathematical, although the solution is not that hard to guess. So what is the procedure? The first thing we're going to, so the idea is to treat HT, which is where this, so T is a small parameter, so we can treat the Hamiltonian part HT as a kind of perturbation, right? And the idea is, first of all, to do what's called a unitary or a canonical transformation. So we will take H and turn to some H prime. This fancy word, unitary canonical, all it means is that the transformation does not affect the commutation relations between the different operators. So after this transformation, which looks a little arbitrary, and it is arbitrary, it's only if you know where you're going that it's smart to do it from the beginning. So someone has to guess it in the beginning and win a Nobel Prize for it. But after someone has done it, we can copy it. But these fancy words just mean that A and A dagger still commute in the usual way that fermions do, or anti-commute. The second step will be to expand in low orders of T. Because T is a small parameter, so we keep only, say, the linear term or the quadratic term, however much we will need. We'll actually keep only the leading order, but we will see that the order that is proportional to T vanishes. So the smallest contribution will be T squared. But we'll get there. And then in the third step, because we anticipate that these single occupancy states will be the ones that are strong, or have a large contribution to the ground state, we're actually going to project the Hamiltonian into the subspace spanned by just these two vectors. And we do this with projection operators. Where this PS projects into the subspace spanned by S1 and S2. So what we're effectively going to do is we're going to throw away, at the very last step, we're going to throw away the double occupancy states. And this will be good for the ground state, because we know that in the ground state, say when temperature or whatever doesn't play a role and you cannot overcome this barrier of interaction with some temperature of some sort, we've already predicted that the main contribution will come from these states, so we're going to throw away all the rest. But this comes at a cost, namely that we now will lose all the information about more excited states. Because the excited states obviously will contain more of the D states. So if you want to predict the ground state, which is usually what you want to do in condensed matter, it's usually the most interesting, then this is good. It's also the easiest to do theoretically. To talk about more excited states, I don't know if any of you are condensed matter theorists, but you're usually told not to deal with excited states because they're way too complicated. Anyone told you that before? Not yet. Okay, so I'm the first one. Well, from an experimentalist point of view, the ground state is more simple, it's more quantum. You get more quantum mechanics in the ground state, which is typical for quantum mechanics. A theorist might use the word interesting, but call it easy. I don't know what theorists do. It's basically nothing we know how to solve. It's kind of a problem because in an experiment, it is very hard to produce a pure ground state. You have to be very cold, basically. And if you can't do that, if your liquid helium isn't cold enough, 4 Kelvin isn't cold enough, okay, then you use a dilution fridge and you get down to millikelvin. So that isn't cold enough, well, then you're screwed. Right? And you always have excitations, which is a common conclusion of experimental articles. We couldn't see the ground state because it's still too hot. So, welcome to physics. Okay, so let's do these 3 steps. I will not do all of the math. At some points in the calculation, I will say math happens. And what I mean by math happens is that you will make the math happen in your homework. So you can feel it in your own blood. Before we start, though, I want to introduce a little bit more notion about these projection operators. This might be something new, so let me give you some feeling for what they do. So let's take a minute to talk about projection operators. So a projection operator that projects into the S states, into the single occupancy subspace, if you apply it on one of the S states, you have to get back the S state. That's the definition of the projection operator. And if you apply it onto a D state, well, then you must get 0. That's the definition of the projection operator. Let's try and think of an operator that does this. So I already thought about it. I'll give you the solution. And let's check that this works. So I'm going to apply this PS onto the state S1. And I have to get back S1, right? That's what must happen. If that doesn't happen, then I'm screwed. So this is 1/2. There's a sum here. There's N1, 2 minus N1, applied on S1. Now, what is S1? That is the state 1001. And then I have to apply the second part of the sum, which is 1/2 N2, 2 minus N2. And that also acts on the state 1001. Okay, so what do I get? What is N1? It takes out the number of particles in site number 1. So how many particles are on site number 1? And how many particles on site number 2? Also 1. So we get 2 minus 1 is 2. Sorry, 2 minus 1 is 1. Divided by 2 is 1/2. Same thing here. 1/2 plus 1/2 is 1. So you get, let's write it out, 1/2 1001 plus 1/2 1001. And that's just the same state 1001, which is S1. So that works. Right? You can check that the same thing happens for S2. And if you applied on any of the D states, well, then either N1 is equal to 2, right? Because N1 is the first site, right? This is the first site, and this is the second site. So either N1 or N2 will be equal to 0, in which case this term, so one of them is equal to 0, gets rid of this part of the sum, and the 2 on the other one gets rid of this part of the sum. So it's always 0 times 1 or 2 times 0. Right? So you can check that this works. And for in the same manner, you can also define a projection operator that takes you onto the subspace spanned by D1 and D2. And in this case, the projection operator is the sum over Ni times Ni minus 1. And this, of course, has the properties that when it acts on either of the S eigenstates or the S Fock states is equal to 0, annihilates them. And if it acts on any of the D states, it just returns the D state. So that's why these are called projection operators. Okay, let's start with our transformation. And for this transformation, I'm going to introduce an seemingly arbitrary operator, which I call F. Sorry, S, D, D, S. There we go. So it looks weird. But actually what this does, if you look at it you stare at it for a long enough time, what this does is it turns an S state into a D state and the opposite. So if you think about it, if this operator acts on an S state, then only this contributes, this doesn't. Because PD acting on an S state is 0. Right? So only this contributes. So you take so you're acting on S1, only this contributes, PS doesn't do anything. HT will do some hopping. What does the hopping do? Well, it'll hop if you can, it'll take, we were in S1, so it'll take this up particle and move it over here, right? And it'll take will it? HT. What am I trying to do? I was trying to turn S1 into D2. Too many hopping terms. I'm hopping around, and then I'm projecting back onto D subspace, which will end up in D2. I have to stare at it a little bit longer, but if you stare at it long enough, you'll see that's exactly what it does. You can write it out, and you'll notice that basically takes an S state onto a D state, and a D state onto an S state. Ah, interesting. I lost it. Okay, let's continue. So what is the, and one thing you should note, or that you will test, this is one of the math happens cases. Math happens, and you can show that the commutator of F with HU gives HT with some prefactor. And this will be useful for later. Okay, now let's do our transformation. So our transformation will be, it's a transformation of an operator, so we have to apply some operation on the left and on the right. We're taking our Hamiltonian, the total Hamiltonian, to H prime, which is equal to e to the minus t times the F operator times H times e to the t to the power F. E to the t times F. I'm going to expand both sides into a Taylor series, and then collect powers of t. So you get the original h minus t times the commutator of f and h, because there's one term which is f times h and one which is minus h times f when you open these pairwise. I think you did this back in QM1. I give it as homework, I remember it. And then the next term will be plus t squared over 2. And you're like, oh, I shouldn't have copied. How dumb was I? I would have known this. I remember it well because pretty much everyone got it wrong 2 years ago. So I remember this question well. I give it every year. And still no one succeeds. They all copy the same mistakes. You're now starting to teach, so you're going to realize that that's what happens, in case you haven't realized yet. Okay, so this is what happens. It's, you know, it's simple algebra. I'm not going to...
You just have to give the right answer.
Have to give the right answer?
No, after you finish
That makes it...
the correct one, and then they'll copy from the...
You should ask this year about copying official answers from previous years and what happens in that case. They had an interesting story in solid-state physics where they copied official answers which were totally wrong. Okay, now I haven't actually collected powers of t yet. I've only written t explicitly, but remember that h is a sum of the hopping term and the interaction term, and the hopping term has a t in it. So what I have to do now is plug in for each h, ht plus hu, and also here. And then remember that ht is linear in t, and hu is order 0, or order 1, order 0, t to the power 0 in t. And then regroup this stuff. And I'm only going to keep up to second order in t. So we get h prime is equal to hu plus ht minus t. F commutes with u minus t. F commutator with ht plus t squared over 2. F commutes with the commutator of f and hu. So this thing here is 0th order. 0th order. This thing here, ht is first order, and so is this t times hu is also first order.
Why is ht first order?
Because ht is equal to t times something. Look back to...
So we don't count u?
Don't count u, what? I'm collecting orders of t.
You are looking at orders of t.
Of course.
U is, you don't look at it.
Correct. Because t is my small parameter. Right?
Means another object, you have t squared with hu, then you should have the same with ht or like x squared.
But ht is linear in t.
So it will be t in the third.
There you go. And this is second order. Yeah, I'll explain what I'm doing. It's really simple math. You're just lost because I've been throwing like stuff at you for the past hour. But actually really simple. All I'm doing, I could make it more complicated and actually write ht and hu explicitly with the entire sum of all the a's and a daggers, and then it would be simple because ht is equal to t multiplied by some sum, and hu is just u multiplied by something. Now my small parameter, remember we're in the limit where u is much larger than t, so I want to expand in orders of t because I can neglect higher orders of t. I cannot neglect higher orders of u because u is already very strong. So I'm collecting all the terms according to how weak they are, right? This is the strongest term. This one is weaker because it's suppressed by 1 order of t. This one's even weaker. And then here I have order t to the third and so on, which I don't even care about. as I promised, the first order is going to vanish because the commutator of F and HU is equal to 1 over T times HT. So that just cancels. Very nice. That just tells us that this perturbative limit is good because the only correction is it's twice. It's depressed twice. And then we can use, what can we use? We can use the commutator again. So F with HU, right? That'll give us HT divided by T, which is order 0 in T, because this is order 1 in T and this is divided by T. So there's no T in the end. And then when I replace this, I lose this T, or one of the T's. So this is commutator of F with HT, which is the same as it says here. Where's the minus sign here? Shouldn't be like that. What's wrong? What's wrong? Must have an error in the sign somewhere. Interesting. This must be a minus sign. And then you get twice the same. No, sorry, it is a plus sign. Because it's minus T plus 1/2 of that stuff. So this is then equal to HU, which is the 0th order, minus T over 2. F commuting with HT. Again, it looks complicated. I promise this was simple math. You see it? Seriously, if I tell you it's simple, it's simple. Not many things are, but this is. Just plugging in this commutator into here. Right? Okay, very good. So this is our H prime. So it's the same Hamiltonian. It contains the exact same physics as the previous Hamiltonian. It's just written in a language that's a little hard to understand. It's like teaching in English. That's the same thing, right? Okay, now comes the final step where we lose information, which is the projection. So let's project H prime onto the subspace that is spanned by only the S states. First of all, you can check actually quite simply in your head that projecting HU onto the single occupancy substates gives 0. That makes sense because the single occupancy states do not have interaction energy. Right? So this entire first term will vanish when you close it with PS on both sides. And you're left with only the second term. And for the second term, let's do this. You're taking FHT, so let's write this out first of all. So the commutator of F with HT is 1 over TU. I'm just plugging in F and opening up the brackets of the commutator. So there's PS, HT, PD, HT, minus minus HT, PS, HT, PD plus HT. All I've done is open up the commutator and plugged in the definition of F. So I have 4 terms because F had 2 terms. The commutator is another 2 terms. That's 4 terms. And now I'm going to use the projection operators. So I'm going to put PS on either side. I'm going to put a PS over here and a PS over here. And this is very convenient because now this term vanishes and this term vanishes. You see why? projecting onto the S subspace, and then projecting to the D subspace. So where am I left? Nowhere, right? So that's 0, and same thing here on the left-hand side, PD, PS. That just goes away. And then on these two terms, PS times PS is equal to 1. So it's just equal to PS, so it didn't do anything. The second one didn't do anything, and the same thing happens over here. So when you do this projection on H prime, what you're left with is minus 1 over u. The t's cancel, this t and this t. And the remaining two terms are exactly the same after you add the ps's. So you have a ps, ht, pd, ht, and ps. That looks very nice. Okay, math happens. You now plug in back in the Hamiltonians and projection operators in terms of A and A dagger. Do a lot of math. And what you should get so you know what? Just this part here, ht, just the middle part. This thing here is equal to t squared. Well, that's the obvious part because each ht comes with a t. And this is equal to t squared 1 plus sum over sigma and sigma prime, A dagger 1 sigma, A2 sigma, and prime, A1 sigma prime, and A2 sigma. So to get from here to here, math happens, but it's straightforward. Just plug it all in, collect the terms. And then when you put back the PS on both sides, math happens again. And you also use a identity of Pauli matrices, which I have given to you in the homework, of course. And then you can show that PS H prime PS. So you can write it in terms of spin operators. Where J is just all of these t squared over u that you get from doing the calculation. So S1 is a spin operator acting on site number 1. S2 is a spin operator acting on site number 2. This is just an energy offset. I could just forget about it, but I'm writing it because when math happens, then this happens. But what I'm showing you, and this is actually the point, is that when you do all this messy stuff, and in the end you project it onto this expected single occupancy state with ups and downs, you get an effective Hamiltonian, or you can map it onto the Hamiltonian, which is just a product of spin operators with some coefficient. And if you do this, if you would do this for a very long chain, so for an infinite number of sites, what you will get is basically the same thing, but with the sum over nearest neighbors Sm dot Sn. And you know this Hamiltonian, the Ising model, and you know what the ground state is when J is larger than 0, an antiferromagnet, right? When J is negative, it's a ferromagnet. When J is positive, it's an antiferromagnet. I think you know this, right? If you don't, then ask Stas. I think he should give you homework about that. I don't know if he did, but he should in statistical physics. So the ground state is antiferromagnetic. So what this is actually a very central result of condensed matter physics, namely that the Mott-Hubbard Hamiltonian, where you have nearest neighbor hopping and on-site interactions, in the ground state, it is equivalent to a Ising Hamiltonian. If you can solve Ising, you can solve the ground set of Hubbard. What this means. This J is called the exchange interaction. You might have heard that exchange interaction is the mechanism behind ferromagnetism. I think I told you that in solid state physics. So this is the strength of the exchange interaction, and here you also have its microscopic details. How does it behave? How does it depend on the tunneling energy and the on-site interaction energy? So it's kind of a microscopic detail of what the exchange interaction, or how strong the exchange interaction is. Okay, take a deep breath. The complicated stuff is over, or the math stuff is over. So this is the time to reset. And we're now going to talk about Wick's theorem. I'm going to demonstrate how it works and prove it, hopefully before 7:30. Maybe not. So Wick's theorem, unlike this stuff, is very simple mathematically, but it's conceptually maybe a little bit challenging, unlike this, which was just pure math. Just looks complicated, but just pure math. So wake the other side of your brain, and let's go ahead. So we're going to consider a product of operators. And we're going to limit ourselves to bosonic case, but the fermionic is exactly the same. The end result is the same. There's some minus signs on the way, but they all cancel in the end. So we're just going to start with bosonic operators. And, well, if you want to torture yourself at home with fermionic, go ahead. So we're going to look at a chain operator, so 4 operators, A times B times C times D, and I'll take a specific example to illustrate what's going to happen. I'm destroying a K, I'm creating a particle in state L, and I'm creating one in state M, and I'm destroying one in state N. That's an example where K, L, M, and N could be all different, or 2 of them could be the same, or they could be all the same. Anything is illegal here. Now I'm defining the normal order of this product. Allow me to not write hats every single time. The normal order of this product, which I write as normal and then brackets of whatever I'm taking. Another option, I think that's what I thought uses, is with these 2 little dots. I hate that notation. Don't tell her I said that. But for people who have messy handwriting, dots get lost everywhere. So I prefer normal order. But what this means is that you take all annihilation operators to the right and all creation operators to the left. So this is A dagger L, A dagger M, AK, AN. Now, the important thing to stress here is that this is not an operation on operators. I'm not taking a string of operators, applying normal order, and then I get this. That's not what this means. This is notation. When I write this expression, normal order of the string, what I mean is this. Okay? Pure notation. We can actually check what the difference is between the original operator, without normal order, and its normal order. And to do that, well, we can simply use commutation relations to shift the stuff around. So AK, AL dagger, AM dagger, AN. So I want to move AK to the right. So I have to use 2 commutators, once with AL dagger and once with AM dagger. So I'll have 3 terms in the end. So I get AK, AL dagger, AM dagger, AN, plus AL dagger, AK, AM dagger, and AN. And one last term is AL dagger, AM dagger, AK, AN. And this thing here in the end, this is the same as saying normal order of what I had in the beginning. A, K, AL dagger, AM dagger, AN. In other words, the difference between the original operator, the unordered operator, and its normal order is, looking right down again, is this thing here. So it doesn't mean that I'm applying this and then getting the normal order. It's notation. And the difference between the operator and its normal order is what we just calculated. Okay, let's introduce the notation of contraction. This will be helpful in a minute. The contraction between two operators is defined as exactly this, the difference between an operator and its normal order. Right? Exactly this, the operator in any order minus the normal order of that case, but this time in the case for two operators. So this is equal either to 0 if A and B are already in normal order, and it is equal to the commutator of A and B if they're not in normal order. This means that I can now rewrite this 4-string example with the notion of the contractions in the following way. So let's go back to, I'm going back to this top line over here. So A, K, A, L dagger, A, M dagger, A, N is equal to, first of all, the normal order of whatever this is, A, K, A, L dagger, A, M dagger, A, N. Plus, so now I have this term, and instead of writing the commutator of AK and AL dagger, I'm going to just write the contraction. So this is plus AK AL dagger contracted times AM dagger AN. And one more, that's AL dagger AK AM dagger contracted times AN. Now, the contraction is the commutator, which is equal to a number, 0, 0, or 1, right? And that means that this is not an operator, it's just a number. So actually, this term is also in normal order, right? Because this is just a number, and now daggers on the left, no daggers on the right. Same thing here. The commutator, the contraction is just the commutator, which is just a number. To get rid of this, and you're left with something that's already in normal order. So I can take this normal order notation and move it over here. That's the same thing, because it already is in normal order, right? Okay, now that I've shown you how this works, I can state the theorem, and then I can prove it in 30 seconds. So what is the theorem? Statement of the theorem. So So we consider some long string of operators, A, B, blah, 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 Z. This is some string of, I don't know, 7,322 operators. Okay? The theorem states that this string of operators, which is in some random order, is equal to the normal order of A, B, blah, 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 Z. So everything is reordered now in the correct way. Plus something I call all contractions. What does all contractions mean? Let me demonstrate this to you with 4 operators. You see that what we have written up here already looks kind of similar. It's the normal order of something plus stuff which has contractions in it. Right? So what this means is the following. If I take an example A, B, C, D, and I'm going to apply, so this is the theorem, and I'm going to apply the theorem onto A, B, C, D. So I get the normal order of A, B, C, D. And then I have to take all contractions. And there are multiple options of taking all contractions. I can either take the contraction of just 2 of them or of 2 pairs. So this is plus all contractions. First option, I can contract A with B and leave C and D untouched. Second option, I can contract A with C and leave B and D untouched. I can also contract A with D. Okay, that's all the A's. Now I contract B with C. I can contract B with D. And I can contract C with D. So that's all of the single contractions. It's again one of those things you have to think for a second. Are these all of them or did I miss one? So these are all of them, right? Hope you agree. And then I can also contract 2 of them. So I contract A and B and simultaneously C and D. I can also contract A with C and simultaneously B with D. Or, there's one more option, C with D and B with C. So this is what I mean by all contractions. This simple, harmless term means this mess. And of course, it's simple to generalize to any number of operators that you have. Right? The last 3 terms, they're the most important ones. They are called fully contracted. For obvious reasons, every operator is inside a contraction. There's no random free operator flying around. Okay, so let's revisit our example, show that this works. Then I'll show you why the Wick's theorem is useful, and then I won't prove it because it's getting late. Do you believe that this is correct? You shouldn't. You should check. Maybe I'll give them the homework. I won't, don't worry. But the proof is simple. It's done by induction, so it's not very difficult to prove. But let's show that this works first of all, because I think understanding or knowing how to use the theorem is more important than proving it. I shouldn't say that actually. They're equally important. Let's do this. So I'm using AK, AL dagger, AM dagger, AN. This is the same example that we already used earlier. And I'm going to apply Wick's theorem to it, exactly as it is written. So it is equal to the normal order of AK, AL dagger, AM dagger, AN. Getting bored of writing the same expression. And now I have to take all contractions. So I have 6 single contractions.
What are we proving?
We're not proving anything. We're applying. We're applying Wick's theorem to this operator. This is A, this is B, this is C, this is D. Okay? I want the proof in my box by tomorrow. Listening. Okay. So I need to try contractions. So the first option is to contract the first two. Second option, aka. It's much easier when you use a computer because you just do copy paste. Contract the first and the third. I can contract the first and the fourth. Okay, so that's the first 3. I can now contract the second and the third. I can contract the second and the fourth. And I can contract the third and the fourth. Okay. That's 6, very good. And now I come to the second line, or the third line, which are the fully contracted terms. There's A, K, A, L, dagger, A, M, dagger, A, N, where I contract the first 2 and the last 2. And I'm contracting 1 and 3 and 2 and 4. And one more, we're almost done. A, K, A, L, dagger, A, M, dagger, where I'm contracting the inner and the outer 2. And close the brackets on the normal order. Now, is this the same as what we found more or less empirically in the first case? So you see here there are more terms. But let's get rid of some of them which obviously vanish. For example, here I'm contracting an annihilation operator with an annihilation operator. That's obviously 0 because one way to see it's already normal order. Another way to think about it is because the commutator is equal to 0. So this vanishes. This is dagger with dagger also vanishes. This doesn't. This doesn't. It will eventually in a second. And this is also A with A and A dagger with A dagger, so that also vanishes. And in addition, some of our contractions are already in normal order. So AK, AM, sorry, that isn't. Where am I? Here, this one here, AM dagger, AN, is already normal order. So this contraction is also equal to 0. See that? Hello. Already equal to 0. What else am I missing? This one here is also equal to 0, A dagger, AN. Right, so it also disappears. And this one here, I have here AL dagger, so this part here is also already normal order. So this one also vanishes. And I think we got it. So up here we have AK, this is the first one. Then this here I've contracted K and L, that's this one here. And here I've contracted K and M, that's this one here. So this works. What about this one? It's also normal order. It's dagger and then no dagger. That also goes away. Yay! Wick works. Why is this useful? Why would I do this?
Why, one question on the second line, the AKAL dagger, the last expression. Why is it normal order, isn't it, when it starts with a dagger and
No, the contracting, this part is equal to 0.
Ah, okay.
Because contraction of something in normal order is by definition equal to 0. Why is this useful? Wick's theorem has one use and one use only, but it is a very important application. And that is computing expectation values of the vacuum state. Why it is important, that's a different story. But let's just say that you have a test question and you're asked to compute the expectation value of the vacuum. By convention, anytime you see some operators inside brackets like this, what one means is that there's a vacuum state, and you're taking the matrix element, basically, of the vacuum state. So if this is what people write, this is what people mean. Okay? It's just the most common expectation value that you could use, that you could write. So what happens when we try doing this? So the point is that only the fully contracted terms contribute. And why is that? Because any fully contracted, wait a second, terms contribute. And the reason is simple. That's the power of normal ordering. Normal ordering means that we always have an annihilation operator on the far right, and then there's an annihilation operator acting on 0, which is 0, so on the vacuum state, which is 0. And even if there are no annihilation operators, then there's always a creation operator on the left-hand side, and that's just the complex conjugate of annihilating. So you have this combination, which is also equal to 0. And because of this, only the terms that have no operators left can contribute to this expectation value. So anything that has an operator left in here, right, this thing can contribute because AN will destroy. This thing can contribute because AN will destroy. Same thing here, same thing here. Or A dagger in this case will destroy you on the left-hand side. The only ones that can contribute are the ones that have no operators left, that have only numbers left. And these are the fully contracted terms. So you see that for our example that we solved up there, this expectation value is just equal to 0 because all fully contracted terms are equal to 0. So this is equal to the sum of all fully contracted terms. For our example, AK, AL dagger, AM dagger, AN, this expectation value is equal to 0, and if you want you can check it by plugging it all in, but I trust that this is quite obvious. Okay, so I'll leave it at this for today. I'll see if I'll prove it next time or not. Let's see how important we feel it is. Questions on today? Yes.
You said that it needs to be contracted to have any results. In order for it to be contracted,
Very good. So it has to be an even number of operators. So you have learned now that if you have an odd number of operators in a product, the vacuum expectation value is always equal to 0. And it's kind of intuitive, because in an odd number, when will this not be equal to 0? When you create and then destroy the same particles. If you have an odd number of operators, that's not possible. So it's kind of intuitive, but this is mathematically the way it works. Questions? Okay, make sure to hand in your homework by tonight, and see you in 2 weeks.